Hello students, welcome to my channel. In this video, we will study the kinetics of the free radical polymerization reaction. Okay, now we know that in the free radical polymerization or simply a polymerization reaction, there are mainly three steps, right? So one is the initiation step, and the second is the propagation, and the last one is the termination step, right? So now in the free radical polymerization reaction, the initiation is carried out by the initiator, right? Usually the benzoyl peroxide is used as the initiator, and in this case I just take the I as the initiator. Okay, here I means what? Our initiator. It is a benzoyl peroxide, and this benzoyl peroxide or the initiator undergoes homolytic cleavage so that we will get the free radicals. Okay, we will get the free radical. So I write the free radical like this. Okay, we'll get the identical free radical, right? So benzoyl peroxide structure is what? It is C6H5, C double bond O, 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 C double bond O, C6H5, right? This is our I. I means what? Initiator. Okay, this is our initiator, benzoyl peroxide. This benzoyl peroxide undergo what? Homolytic cleavage. So whenever it undergo homolytic cleavage, how many free radicals you obtain? You will get the 2, right? 2 free radicals are obtained of similar kind, right? So this is what you get, C6H5. So that is why I written the 2R free radicals, because these are same, right? This is what indicating the free radical that are obtained by the decomposition of the free radical, okay, obtained by the decomposition of initiator. Now, the rate constant for this decomposition reaction is Kd. Okay, Kd is what? Kd means it is a rate constant. The rate constant for decomposition of initiator. Okay, the Kd means a rate constant of initiator. Now, the rate of the decomposition of initiator. Okay, the rate of decomposition of initiator. As soon as we write the reaction, no, we have to write the rate. Okay, so the rate I represent by capital R. Since it is a decomposition reaction, I write it as RD. Okay, RD means what? It is the rate of decomposition of initiator. Is given by what? The rate is given by the rate constant multiplied by the concentration of reactant. Okay, so here rate constant is Kd and our reactant is what? I. Okay, I write concentration of I 2 times. Okay, so RD is equal to what? 2 Kd concentration of I. Okay, I take this equation to be equal to 1. Okay, so why it is 2 is there? 2 is used because in this equation you can see, or in this reaction you can see, there are 2 free radicals are formed. Okay, that is why I written 2. Okay, the 2 means what? It is the 2 radicals are formed. Okay, it is indicating 2 radicals are formed by the decomposition of one initiator. Okay, now we know from the Arrhenius equation, okay, from the Arrhenius equation, we have the this equation, that is K, the rate constant, is equal to the AE to the power minus EA by RT. Okay, we have this equation and name this equation to be equal to 2. Okay, now here this is a rate constant. No, I write it as Kd. Okay, this Kd, rate constant for the decomposition initiator, is given by A into exponential to the power minus EA by RT. Okay, where A is what? A is our constant called as frequency factor, EA is the activation energy, R is real gas constant, and T is the temperature. Okay, you need to write every terms here. Okay, where write what is a frequency factor, what is EA? It is a activation energy. What is R? It is a real gas constant. T is a temperature. Okay, after writing every equation, you need to write the terms that are involved in that equation. Okay, okay. Now, what I do is I substitute the equation number 2 in the equation number 1. Okay, so in the equation number 1 you can see that there is a KD, right? So in the place of KD I am just writing the equation number 2. So write substituting equation number 2 in the equation number 1. Okay. Okay. So I get RD is equal to what? 2. In the place of KD I am writing A E power minus EA by RT into concentration of I. Okay, this is the equation you get. So name this equation number 3. Okay. Now, what this equation state is that this is the rate of decomposition. Okay, rate of decomposition increases with the increase in a concentration of I. Okay, as the concentration of the initiator increases, the rate of decomposition also increases, and also this RD increases as the temperature increases. So this RD depends on what? It depends upon the concentration of I as well as the temperature. Okay, as you increase the temperature or as you increase the concentration of the initiator, the RD, the rate of the decomposition of initiator increases. Okay, now we generated the free radical by the decomposition of initiator, right? So first step is the initiation. Okay, initiation. Okay, so far we studied the decomposition of initiator. Okay, by the decomposition of initiator we got the free radical. Which free radical we got? It is the R free radical. Now in the initiation step what happened? That free radical attacks the monomer, right? So it attacks the monomer. Okay, R dot means what? It is the free radical generated by the decomposition of initiator. Okay, M means what? It is a monomer. Now what happened whenever the free radical attacks the monomer? The free radical, this dot is there, no? That will shift to the monomer side. Okay, the free radical that is present on the this one will shift to the monomer side. Okay, how? It is like this. Okay, now you can see that this dot is present on the monomer side. Okay, I take this equation to be number 4. Okay, so now this is the initiation step. Okay, in the initiation step what happened? The free radical attacks the monomer. Okay, so that you will get the initiation step. Okay, so I write the rate for this is Ki. Okay, Ki is what? Rate constant for the initiation reaction. Okay, you can write here Ki means what? It is the rate constant for initiation reaction. Okay, after writing the equation, what I told, you have to write the rate. Okay, the rate of what? Initiation. So rate of reaction is given by what? It is rate constant multiplied by concentration of reactant. Now Ri representing rate of initiation is given by Ki, rate constant, multiplied by what? It is a concentration of reactant. So here you have 2 reactant, so you get this. Okay, well, now the equation number is 5. Okay, name it as equation number 5. Now free radical, whatever it is generated by the decomposition of free radical, it is very reactive. We know the free radicals are intermediate. These are very reactive, right? So once the free radicals are obtained by the decomposition of the initiator, it will attack the monomer. Okay, it will attack the monomer, right? So what I can say is that the rate at which the free radicals are generated is equal to the rate at which they are disappearing. Is that so? Okay, since the whatever the free radical you get is highly reactive, right? So once they obtain it, in this step, once they obtain it in the decomposition of this initiator, they soon attacks the monomer, right? So the rate of their generation is equal to their disappearance. Okay, what I mean is the Ri is equal to Rd. Okay, why it is so? Because the free radicals are highly reactive. The free radical generated must be equal to the rate at which they are attacking the monomer. So these rates must be equal. This is equation number 6. Okay, now you have the equation for the RD, right? So substitute for this one. We are not substituting here. Okay, so keep Ri as such. In the place of RD, we named it as equation number 1. From the 1 you can substitute for RD, that is 2 Kd into concentration of I. Okay, this is our equation number 7. Okay, you get this. Okay, now this equation 7 is holds good when every free radicals that are generated are efficient in attacking the monomer. Okay, this equation is valid only when all the free radicals that are generated by the decomposition are effective in attacking the monomer. But in practically it is not observed like that. Okay, because some of the free radicals are undergoing some side reactions. They all the free radicals do not attack the monomer, only some of the free radicals are attacking. Okay, so this equation doesn't valid in this case. So what we can do is we can modify this equation like this, by writing this term F, okay, Kd into concentration of I. Okay, so this is our equation 8. Now this is valid. Okay, why this is not valid? Because this is valid when all the free radicals are generated are effective in what? Attacking the monomer. But in practically what we observed, some of the free radicals are wasted because of the side reactions. Okay, so we are modifying the above equation like this by writing the F. Okay, so what is F there? F is it is nothing but it is the fraction of the free radicals that are effective in attacking the monomer. Okay, what is F? F is what? It is a fraction of free radicals that are effective. Effective in what? Effective in attacking the monomer. Attacking the monomers. This value of F, okay, the value of this F ranges from 0.6 to 1. Okay, so the value of F is between 0.6 to 1. That means if the F value is 60%, okay, suppose if the value of F is 60%, that means out of 100 only 60 are effective in attacking the monomer, while other 40 is there, no, that is wasted because of some side reactions. Okay, well, now we will write the propagation. So far we studied the initiation. In initiation, what happened? The free radical generated by the initiator attacks the monomer, right? So now the propagation. Give the side heading, the propagation. So in propagation, what happened? The free radical that is generated in the initiation step. So what is our initiation step? This is, right? In the initiation step, we got Rm free radical, right? So that now will attack the another monomer. Okay, that attacks the another monomer, and what happened? The growth of the polymer chain increases like this. Okay, the free radical initial present over here is shift to this monomer now. Okay, if you take another monomer, what happens? If you take another monomer, the growth of the polymer chain increases. That's it. Okay, like this. Now suppose if I take the n number, what happens? N number of the monomer, then the polymer chain increases, right? The growth takes place. You will get something like this: M free radical. Okay. Now let the Kp, okay, the Kp be the rate constant for the propagation step. Okay, what is Kp? Kp is a rate constant for the propagation step. Now what is the rate? The rate is represented by Rp. Okay, Rp means it is a rate for the propagation step. Is given by what? Rate constant multiplied by the concentration term of the our reactant. Kp, concentration of M free radical and concentration of M. Okay, so this is our equation number 9, right? So this is our equation number 9. Okay, so Rp is what? It is Kp, concentration of our reactant. Now if you see here, this is what attacking the another monomer, right? You can write in the place of M free radical, no, you can write all these terms also, but why I written only this much? Because in the final equation, no, it look little lengthy if you write everything. So I am writing only M free radical, okay, because M free radical is actually attacking the another monomer, right? So I am writing only that much. Okay, if you have confusion, you simply write everything. Kp into concentration of M free radical into concentration of M. Okay, like that also you can write. But for simplicity, it is better if you write M free radical. Okay. Now from this equation, okay, from the equation number 9, you can write the concentration of M free radical. Okay, what is M concentration of M free radical? Take these two terms to the denominator. Okay, you get Rp divided by Kp into concentration of M. Okay, this is our equation number 10. Okay, these two terms are carried to the denominator. You get this. Okay, now propagation is done. Next is the termination. Okay, termination, wherein the growth of the polymer chain terminates. Okay, so now suppose if you have the two growing polymer chain. Okay, I just take this one only, M free radical, M free radical. Okay, this is the one growing polymer chain. Now suppose if you have the another growing polymer chain like this, N, R. Okay, just what it I write is I just written in the reverse way, M free radical. I just written the same thing in the reverse way. That's it. This is one just to differentiate the two growing polymer chain. Okay. Now what happened? These free radicals combine like this, so that termination occur. Or Mn1 Mn2 R. Correct? So there is a formation of the covalent bond between the monomer like this here. Okay, between the two growing polymer chain, what happened? There is a formation of covalent bond and the growth of the chain terminate. Okay, so since it is a termination step, I write it as Kt. Kt means it is a rate constant for the termination reaction. Okay, then what is RT? RT means what? RT is a rate of termination. Okay, termination step. It is given by Kt into concentration of M free radical into concentration of M free radical. Okay, twice, because we have two, right? Same, right? These are actually a same. So 2 Kt, concentration of M free radical, and concentration of M free radical. Now you can write this as 2 Kt concentration of M free radical square. Okay, we have 2, right? So M free radical square, concentration of M free radical square. Okay, RT. This is our equation number 11. Okay, now at steady state, means at the equilibrium. Okay, the number of chain growth that is started must be equal to the number of chain that is arrested. Correct? How many number of chain that is started? No, that many number of polymer chain should be arrested. Correct? It should stop growing. Right? So Ri is equal to Rt. Okay, at steady state, the number of chain growth that is started or initiated must be equal to the number of chain that is arrested. Correct? So Ri, initiation, rate of initiation, must be equal to the rate of termination. Okay, so substitute Ri and Rt. So we have the Ri equation, right? From where? From equation number 8, I guess. Okay, from equation 8. Yes, from the equation 8, and for the Rt we have 11. Okay, from the 8 and 11, substitute for Ri and Rt. Okay, we have Ri 2F Kd concentration of I. Right, from the equation 8 I am writing 2F Kd concentration of I. And for Rt we have here only 2 Kt concentration of M free radical square. Okay, 2 cancels. Then write as such Kt concentration of M free radical square. Okay, from this equation write M free radical, concentration of M free radical. Okay, from this equation only. So you have F Kd concentration of I. Take this to the denominator Kt, and here square is there. No, whenever you take the square to the other side, it becomes a square root. Correct? Or simply 1 by 2. Correct? No. If you take the square root, so what happen? 1 by 2. The square, whenever it go to the other side, it become a square root. Okay, now we have the equation for this. From where? From the equation number 10. Okay, equation number 10. From equation number 10, What we have? We have Rp Kp by into concentration of M, right? So this is the equation we have from the equation number 10. Substitute in the place of concentration of M free radical. Okay, then write the right hand side as such. F Kd by Kt into concentration of I power half. Okay, or you can simply write square root also, no problem. And then what you do, keep Rp here only, and these two terms are taken to the right hand side. Rp is equal to Kp into concentration of M. Then you have F Kd concentration of I by Kt power 1 by 2. Okay, 1 by 2. Now you can this is the final equation itself. You can simplify this one. Kp Kd Kt power half. Okay, power half, and F concentration of I power 1 by 2 into concentration of M. Okay, I just written in a simpler way, or you can stop here also, no problem. Okay, Rp equal to, okay. Now here you can see that this Rp, the rate of propagation step or rate of polymer formation, okay, it is directly proportional to what? It is directly proportional to the concentration of the monomer, as well as it is square root of concentration of I, correct? So Rp is what? The rate of polymer formation is directly proportional to the concentration of a monomer, as well as it is directly proportional to what? Square root of concentration of initiator. Okay, so this is the kinetics of free radical polymerization method. Okay, if you have any doubt in the derivation of this kinetic, you can ask in the comment section. Okay, hope it is clear. Thank you for watching.